just let you start straight away, Patrick.
Thank you, Rail. Thank you for this invitation. I think it's the concluding talk of this very thrilling workshop, so I would like to thank really the organizers. I really enjoyed all the workshops I participated to, and I thank the audience for staying at the last talk on the last Friday. So what I'm going to talk about is a tomography problem, which is a dual of the most popular one, which is the one of traffic estimation, is to locate congested links in the internet, essentially. It's a work which I have done, started with Hung, so this afternoon you see a lot of work with Hung Yuan, so right now who is at University of Adelaide when he was at EPFL, and extended with Denisa Gita, Maciej Koran, and Katerina Argiraki at EPFL. So let me give a brief introduction to the problem of tomography in networking. So essentially there are two approaches that you can use. The first one is the one you use if you have direct access to the network infrastructure, is passive monitoring. So if you are allowed to tap the different links in your network, that's of course the best thing you can do, is simply to spy, if you want, traffic flowing on some particular link. So you have direct inference, you monitor traffic at various points in the networks. It's non-intrusive, so you really get the statistics non-perturbed, and that's really a big advantage. But of course you need to own the approach. So you can do that if you work for a network operator, but not in academia. Academia, you need to take anybody's approach, so essentially that's what I'm going to work with here. It's active monitoring, so you do non-direct inference. You inject probing packets and you retrieve them at various endpoints in the network, and that's already things we have seen in previous talk today. So it's intrusive. Essentially your statistics is perturbed by the traffic you introduce, and that's what Matt explained earlier this afternoon. But you don't need to have access to the network, so you can deploy such systems without having actually to be a network operator. So what we want to do is to diagnose a network using end-to-end probing mechanism, and essentially here what we would like to locate is links that are lossy, so whose, and more even better than that, to identify the loss rate of the different links. So we would like, from end-to-end measurements, by sending probes from one endpoint to the network to the other part of the network, to try to locate these lossy links. So the general setting is as follows. So I will assume throughout the talk that the network has a known topology. In other words, we measure that with trace route. And well, as Walter explained this morning, we are confronted with all the problem of in real implementation of trace route. In simulation, of course, it's another things. And so what we don't know is the loss rates of each of these different links, and we like to infer that by measuring how many probes are lost on different paths in the network. So the same thing as the complement of the link loss rate is transmission rate. So we have three unknowns here. And what we can measure is path transmission rates. So essentially, if we have a path from A to B, we can count how many packets are sent from A and how many are retrieved from B, likewise from A to C. And from that, we try to infer the different transmission rate. So we work all the time with the routing matrix. A routing matrix is a binary matrix that simply tells me which links belong to which path. So all the links are represented by a column in this matrix. All the paths are represented by a row in this matrix. The assumptions we make, so first is that this routing matrix is known perfectly, so no noise on that, at least in theory. And to avoid trivialities, all columns are distinct. It means simply that you can have, you can identify links from the measurement. So it's if you have a pair of links on which all the paths traverse exactly the same pair of links, of course you cannot distinguish each link from end-to-end measurements, and in this case, in the routing matrix, you would have two columns which are identical, and all columns have at least one entry, because otherwise, if a column would be only zeros, well, it simply means that this link is not present in the measurements. The second assumptions, which is key here, and actually what Walter explains might be wrong, because that's what we infer from measurement, is that we have link independence. Essentially, the transmission rate on each of these links are assumed to be statistically independent from each other, but non-identically distributed. And that's an assumption which is often implicit in many tomography work, and which is not true in reality, because the internet is very heterogeneous. And finally, a technical assumption is that all scheduling on all the links is done identically, so all paths experience exactly the same loss rates for all the different paths. Now, the first approaches, it's an old problem, so it's already 10 years ago, was to use IP multicast. So essentially, if you have IP multicast, it means that packets transmitted from A to B would be first sent in A to C, would be first sent on this link and then duplicated at this link. So what I have from A to B first is simply that I can count how many packets have gone from A to B, and since I have statistical independence, the two random variables, I can take a product, so taking the log, I have a linear relation. And I can do that for the other path, and I can do that also for a multicast situation in which I count the number of packets which have been received both by B and by C, since packets are only duplicated here at this middle router here. So I have three equations that are all linearly independent, and so in this case, I can inverse the problem and find directly the solution. Unfortunately, multicast is not deployed in the internet today, or very little deployed internet today, so I cannot make use essentially of the third equation. Essentially, if A transmits packets to both B and C, which are packets exactly of the same flow, well, it will open two unicast flow, but it means that a packet from the first flow might be lost on the first link, and of the second flow might traverse, so there's no perfect correlation. Essentially, I do not have this third equation. And so I end up with a set of equations which, for all non-trivial topologies, is always leads to a rank deficient routing matrix here, so an ill-posed inverse problem. And so I have this kind of problems where the routing matrix is not of full rank, so I have something which is underdetermined, and so I cannot solve it in general. Now, instead of working with the log of the transmission rates and the log of the transmission rates on the path and on the links, I will replace this by xi's for the links and yi's for the measured quantities on the path, so that I have Rx is equal to. Now, what are the different solutions? There are plenty of solutions that have been proposed. The first one is to emulate multicasts. Multicast allows you to achieve a perfect correlation, because packets transmitted on the common links are exact, have a correlation of 1. It's the same packet which is only duplicated here. How to emulate that? Well, it's to hope that the conditions are sufficiently close when you send packets back to back, that two packets sent in a very short amount of time experience exactly the same delay. So you use probe trains in which you send packets back to back and hope that they emulate multicast quite well. So exploit this temporal correlation. But of course, it's an emulation. It's not as perfect as a perfect multicast. And so it's more sensitive to cross traffic. In particular, if you have very long path, well, you can have cross traffic later in your network. Okay, but that's one of the solutions. Another approach has been to either group links, or to, instead of trying to find the value of these different transmission rates, to see if they are above or below a given threshold, in which case you have a Boolean tomography instead of the usual tomography. Now, what we are going to do is actually to look still at trying to find x1, x2, x3, so the log of the different transmission rate here. And so a first approach that comes to mind, of course, to use a pseudo-inverse. So you replace R by the pseudo-inverse R plus, and you're trying to find a solution. Of course, you can do that, it's fine. The problem is that the rank of R is actually much smaller than the real rank. So the effective rank, there's been work done in particular by well, Eric and Mark and Markovella and their co-authors, is that actually the effective rank, so if you plot the singular values, well, there are very few singular values that are high, and very quickly the singular values become very low. What this means is that if you compute the pseudo-inverse, it's very sensitive to small singular values, and thus to noise that you would have in your measurement and also in the matrix R. Remember that we assume here that R is perfectly known, but that in practice it's something you measure, and from the talk of this morning you know that measuring this with trace root is extremely noisy, so the solution will be very sensitive to noise and will often be a bad solution. So what people do, actually authors in Sigmatrix 2007 have proposed to replace this solution by adding a regularization term. And so instead of computing directly the pseudo-inverse, they minimize the sum of two terms. One is the error between, so Rx minus Y, plus regularization terms that regularizes the solution and eliminates some of the noise. Which is fine, especially in two norms. It's something which works pretty well. The thing is that in the internet, very few links are actually lossy. So most of the links have really a zero loss rate. And this penalty here does not penalize that much, does not force many entries to be equal to zero. If they have small values, they will add very little to this penalty, and so we will have something which is pretty far from reality. So what would be better is to replace this two norm by zero norm, but then the optimization becomes very difficult to carry on. So people use one norm as a trade-off between these two, and that's a technique which has been used in this Sigmatrix paper, which we call norm technique, just by here. The question here is that essentially you look at a solution which will be sparse. So essentially that minimizes the number of entries here which have a very large value. Yes?
The two norm of Rx minus Y here. The last one. It's a two, no?
I'm not sure. I'm not sure if they. Okay, maybe I did a typo, but I'm not sure if they use a two or one norm. I can remember that. I think it's one norm that they used in that paper. I wouldn't be able to tell you why the two or the one norm for this first term. I mean, for the regularization term, yes, but not for the first term. So the norm technique. Now, this is a quite natural approach to these problems if you have noisy values here for R and Y. The problem is that it puts a lot of emphasis on finding a very sparse solution, so very few entries which are close to zero. And so here xi, sorry, I forgot to say xi equal to 0 means that the log of the transmission rate is equal to 0, so you have a zero loss rate essentially. And in the internet, typically if you have this solution here, it will blame very quickly, put a high value on x1 compared to x2 and x3. If these two links are access links, actually these links are going to be much more likely to be lossy than this link here, which would be the core link. And so you don't exploit much knowledge about the structure of the network, which typically means is that many paths actually crosses core links in the center of the networks, but these links at the core of the network are typically very well engineered and are non-lossy. It's much more often the access links which are lossy, that are crossed by much fewer paths, and so typically this solution will put a bias towards the core links, which shouldn't be the case. So the one norm solution, so I don't think it's typo, I think it's really the one. The bias towards a sparse solution might be wrong in some cases. Okay, so the second approach we took is to see typically, so that most of the links have a negligible loss rates. And the second one is to work with variances. So congested links have not only, of course, a high loss rate, but they have also a loss rate which is extremely bursty. You don't have a loss rate which is high constantly or which is very low constantly. And so typically if you plot the variance of a loss rate versus the average of a loss rate, you get a very clear relation which is monotonic between the two. And so what we're going to do is try to identify variances. Why is it useful to identify variances? Because variances of the loss rates of links allows us to play with covariances and correlation, spatial correlation between different links, and so that's something that we can do. So we add to our set of assumptions a third assumption, which is that the variance of this xk is a non-decreasing function of the mean value of this xk. So what we are going to do is we try to identify those links whose variance of the loss rate is very small, and since if the loss rate does not fluctuate, so if the variance is very small, it means that the loss rate itself is very likely to be very small as well. So we will take the heuristic of replacing the variance of the loss rate by the actual realization of the loss rate and making it equal to 0. And so that's something we can do in multiple steps. So we call this LIA algorithm. We take multiple snapshots to, from the measurements, evaluate the link variances, and then if we know the link variances, we can assign 0 loss rates to links with the smallest variance until we have a linear systems of full rank. Okay, how do we do that? So coming back to our canonical example, so that's what we have so far as equation, 3 unknowns, 2 equations. So the first order equation, if I take the expectation of this, is trivially this. Second order equation is equal to this. Since these x1, x2, x3 are all independent, I get here a variance which has a non-zero terms, only the variances, so all the covariances are 0. But the different path transmission rates or log of transmission rates, they have correlation which is just due to the fact that I take path which overlaps on some of the links. And that's what I'm going to exploit just in a moment. So instead of writing this equation as RV R transpose is equal to S, I will put all the unknown here, which are the different variances. Instead of being in a diagonal matrix, I put them in a vector, and I will put that in a vector as well. That's actually an approach which has been used initially for traffic matrix estimation, so to work with augmented matrices. So from R, I construct a matrix where I take the product of all possible rows of the matrix R. So typically that was the matrix I had before. Well, all possible pairwise product of different rows I can construct will give me the augmented matrix here. And writing V as a vector of the different variances of the different loss rate, B as the vector that contains all the entries of the covariance, so all the variances and all the covariances of the rows, of the path I and j that corresponds to the product of the different rows, I can write this equation again as a system of linear equations. Now what is nice with that is that if we cannot identify first order moment, we can identify second order moment. So link variances can be uniformly identified from end-to-end measurements. In other words, this matrix here is always of full rank. If I have all the assumptions I had before, so link independence in particular is the key assumptions, and I know the routing matrix, of course, and the additional assumptions we cannot avoid so far, is that there is no root fluttering. Root fluttering means essentially that if I have two paths, one here the blue and the other one the red, they cannot separate at some point and remerge at some other points later on. That is what we call root fluttering. And these are situations that unfortunately do happen in the internet. If you take load balancing, typically you would have something like that. So here we assume that if two paths merge at some point, they can merge, they stay together, and then they separate, they will never again merge again later on, which is key for the proof of this theorem. So the proof of the theorem, well, essentially it's easy in the case of a tree. It's a little bit more difficult in the case of a mesh network. So if I have a tree, well, what you do is you pick a branch of a tree. Say, for example, this tree here is rooted in B. You pick a branch of the tree, and you arrange a column of the rooting matrix R and A so that the n first columns correspond, remember that columns correspond to links, correspond to the n links of that branch of the tree. And then you consider one link after link, the edge after edge of this branch here. So you begin first by the first edge here. So there is a, since all these links appear in the tree rooted at B, it means that you get path going over all these branches of the tree. So in particular, there is a path that goes over the branch starting from 0 to the end node here. And you have another path that separates from the first one at node V1. So in this case, of course, since you have these two paths that traverse the first link but no other link, taking the product of the corresponding row I and I prime corresponding to path Pi and Pi prime, you will get something which is 1 and all zeros. In other words, the columns corresponding to link E1 must be independent from all other columns. And then you continue like that by induction. So if you assume that this is true up to k, well, you take the link here, the k plus 1 link, and you assume that all the first columns here are linearly independent from all other columns. And again, you find a path Pi and another one Pi prime that's separated at this node. So if you take the product of the two rows representing these two paths, well, you will get ones for the first entries and 0 elsewhere, which means that, again, I have linear independence of that column from all other columns in the matrix, and you continue like that for all possible branches. For a mesh, well, and so this has been proved also like more at the same time, actually, but with a different technique in this paper. For a mesh, it's a little bit different. You would like to pick a tree out of your mesh against rooted in B, apply the same principle, which would be okay, except that if you pick a tree, for example, this tree here, you might have that all these links, actually you cannot distinguish them from the drawing, and it's normal that, that you cannot distinguish them because these different links would be traversed exactly by the same path originating from B. They cannot be distinguished from the beacon in B, since all the path going to this node or this node must traverse all these different links. So you cannot infer the link loss rate if you had only this tree. But you might have another tree rooted in another beaconing node A, where actually these different links are separated by other path here. So you could have a path going from A and then going this way, and so you could distinguish them. So you need to take care about these virtual links. They appear in a tree rooted in B as one single link, but in fact they are not a single link. And so that's the additional complexity that we need to take. So what we do is simply to first realize that if I have links that appear on a different path of the tree, they must be independent, because if I have different paths belonging to the same tree, necessarily they will take different branches at some point, and if I use my previous result, I know that they are all linearly independent. So if I have linearly dependent edges or links here in a mesh network, they must all appear on a single branch of a tree, say this branch here, and assume, for example, that E1, E2, E3, E4, and possibly other links might be dependent link. And then you assume that you have these links, and you make an observation that you will use repeatedly, is that any path, any other path, so all these links belong to a single path, which are Pi, and so then you assume that any other path, Pi prime, that traverses one of these links must also traverse either the link of this dependent set which is located before or after. There might be other links which are not in the dependent set in between. The thing is that we can all order them since they are on a single branch here rooted in B. And this would mean that if I take the product of the row corresponding to the path pi and the row corresponding to the path pi prime, well, I would get one entry which is equal to 1 for the link Ek, which is shared both by pi and pi prime, and 0 for all the other links in this dependent set path Ek. And that would be a contradiction, because then this column corresponding to Ek would not be dependent on any other columns in the dependent set, which is impossible, unless I would allow this path to join later on another dependent link, but that's something I have excluded because I don't have any root filtering. So any path pi prime that traverses one link must also traverse either the link before or the link after in this set of dependent links. So I will use this fact. So I take first the two first links E1 and E2. It's easy to see that since I must distinguish these two links, there is one path, let's call it Pi1, that traverses E1 but not E2, or traverses E2 but not E1. Because if all the paths were either traversing both E1 and E2 or not traversing E1 nor E2, I would be in a situation like this where I wouldn't be able to distinguish the loss rates of each link. And so applying these two facts means simply that I must have a path Pi1 that traverses E2 and E3. Same reasoning, there must be a path that traverses exactly either E2 or E3. If it traverses E2, then it must also traverses E1. But then again, I have a contradiction. I apply exactly the same kind of reasoning. If I multiply the corresponding row corresponding to this path and this path, I will get a 1 for this link which is shared by the two paths, and 0 everywhere else for all the link in the dependent set, which again would be a contradiction. So I cannot have the path here. I must have the second path Pi2 that traverses E3 and E4. And I continue this way until I find a path that traverses the last link of my dependent set. But then it would need to traverse another link of my dependent set, which is a contradiction because I have a dependent set which has at most, sorry, forget belong here, that has at most m links, and so I have a contradiction which shows that I cannot find a set of dependent links even in a mesh network. So what this tells us is that variances are identifiable from end-to-end measurement. And so we can calculate the link variances using the covariance. Here it's trivial, of course, because I have here three unknowns, the variances of these three links, and I have the variance of the measurements I obtain along the first path, along the second path, and then the covariance on the two paths. And indeed here I have three linearly independent equations, so I can sort the different links according to the variance that I compute. And the heuristic is that links with small variance are likely to be less congested than links with high variance. So if I do that, well, if the variance of x1 is the smallest one, I will simply, coming back to the original equation, replace this equation here by the same ones where I cancel the first column here and the first unknown, and I can solve because I have a system of full rank. Now, if I apply this like this, then of course I might have some problems. For example, here I have 7 links, 4 paths, and I assume that these are the results of the variances I have obtained, and they are obtained this way. So 5, 6, and 7 are the smallest variances. I approximate their actual rate by 0. But if I do that, of course, I don't get necessarily a matrix of full rank. I have something which is all of 0, so I would need to delete some additional row and some additional column, and again until I have something of full rank. So I decrease the rank of R and I lose information, so I cannot apply it that way. So what we do instead is to pick the links in decreasing order of their variances And so if the third link is the one having the largest variances, and keep them in the left part of the matrix as long as it is full rank. So as long as these vectors are linearly independent from the previous one, I keep adding them. So this one is not. So this one, even though it has a variance which is the third one in the order, I will put in second part of the matrix, and I will approximate its transmission rate by 1 or its loss rate by 0. And I continue this way till I get a matrix here, first part which is a full rank and whose rank is identical to the rank of the original routing matrix. And then I approximate the second, so the loss rate of all the links which I had to put outside the left part of the matrix here to 0 to solve finally the system. So instead of doing this equation here, I apply again the regularization term. That's because I still keep noise, of course, on the measurement and on the routing matrix. And I solve the problem this way. So there are three techniques we can compare here. The first one is to directly apply a regularization term and solve directly this without looking too much at the topology of the network and how this routing matrix is and the variance that I could have. The second one would be to, well, simply look at the variances and decrease the number of unknowns until I have something of full ranks. And the third one, which is a kind of mixture between the two, would be to still look at links, sorting them according to decreasing variances to get real information from what I get in the network, and then to use these decreasing variances to order the links in such a way that the links with the highest variances appear in general here, but not always. I keep them so that the rank of this matrix here remains equal to the rank of the other matrix. Then I set all the unknown variables here to 0, and I solve. I could solve by inverting directly, but since I keep noise on the routing matrix and measurements, I use exactly the same approach as before as a regularization, but using only a reduced matrix that keeps the structure that I have, which was not used before. If I do that first on simulation, well, that's the detection rate, so the fraction of congested link correctly identified as congested. Okay, I didn't speak of this method here, which is a variant of the norm solution. So doing, of course, the best of both worlds will get me the highest detection rate. At the same time, it will keep me a false positive rate, which is very, very small. So this is, okay, some additional results that we can have. So this is the absolute error between the value inferred by the algorithm and the true value here when the number of lossy links in the network goes from 5% to 30% of different loss rate. And so it's something that we have implemented. We call it Netscope. So to give you some numbers for the size of the network, so we use it on Planet Lab. So with all the default that Planet Lab has, so it's deployed on 400 Planet Lab nodes. So we measure the network topology using traceroute, so it's a noisy measurements. We probe the path using UDP Unicast packets, and so the server runs at EPFL and processes the measurements. So there are three implementation issues. The first one is that R remains a very large matrix. It's a 3,000 over 4,000 matrix, so it's actually most of the time it's taking still in the computation of the solution and not on the measurements. And of course, all the problem of Planet Lab that Matthew described a little bit earlier, typically that they're highly loaded. So right now we have that. We have also that implemented in one client in a major ISP in Switzerland. So it works is essentially we have the server here. The beacons are deployed everywhere on the planet, and the request, so the schedule for the different probes that need to be sent from the different beacons are regularly sent from the network operation center. That includes typically how many probes need to be sent in a given time interval. Not the precise times, but the number that needs to be sent over a given period of time, and which path should be taken. We cannot take all the possible paths simply because it would overload the system. So we need to choose which path needs to be taken. And so, well, these paths so send UDP probes from one router to the next one throughout the network. And the topology is measured using traceroute. Okay, and so the beacons report to EPFL at periodic interval of time, typically every 10 minutes, the request, and the computation of the link rates is done centrally here at EPFL. So, hoping that I can show you some of the, so this was the map half an hour ago. If you see something here. Okay, so that's typically okay. The map that we had. Oops, that's always the demo effect. Okay, let me. I've been disconnected from the. Okay, so that was the fixed image. I'll try to. So that was the one of yesterday at the same time. So typically, the measurements are done. So it's all the links here in pink would be the links where loss rates have been computed to be above 0, and all the blue ones is where it's exactly 0. So you have that this link is so a few links are in pink typically, but they fluctuate over time. So it would be interesting to see how it was, but I was disconnected from the login, so I would need to relog on this directly. Okay, so if I go back, is it F5? Oh, sorry. Okay, so here I was. So, of course, the problem there is that we don't have the ground truth of that. So we can only do a cross validation, and typically we get that kind, so that we have up to 20% of error in the cross validation for, I mean, up to 20, or if almost 80, 75% of the path are correctly predicted, cross validated using the approach. Some observation we could make using this tool is that typically 83% of the links in our data set, so in our measurements, have a loss rate which is below 0.1%, and only 4% have a loss rate above 5%. And the type of lossy links, most of the lossy links are, as one can expect, inside an autonomous system would be typically access links inside an autonomous system. There would be a few links between different autonomous systems, which also can be expected. Typically, peering links are most loaded, and we found only few and with a relatively low loss rate inside the core of an autonomous system. So, as a summary of the talk here, we'd say, so first order moment of loss rate is an ill-posed problem. You cannot solve that, but you have a lot of variables you can work with, and typically spatial correlation provide additional information that lead to identification, even if you don't use any temporal information. So we use only spatial correlation, no temporal correlation, because it's very difficult to use in very large systems. Synchronization between hosts that would be in Australia and in Europe, for example, is almost impossible to achieve, I think, right now. And so higher order moments, it's something which is known for traffic matrix identification. Well, it's the same property that holds here for network performance tomography, so the dual problem, are identifiable in a mesh network. Second order moment, so as sufficient to identify exact loss rate for the most congested links. And I will conclude my talk here, thanking you for having stayed here until the end of the workshop.
Questions? So I have a question. So
Yes.
you mentioned at the beginning that the L1 normalization, the regularization is inappropriate because
The
it just goes.
The L2. Well, the best would be the L0 because that would be just 1 if I have a non-zero loss rate and 0 otherwise, but then it leads to a non-convex optimization. But then L1 is better than L2, especially because if I go over L2 or if, you know, LP with P being higher, I will put little penalty on loss rates which are non-zero but small values. Essentially, they will count for nothing in the sum there. And very often, these non-zero terms are actually exactly equal to 0. So I would like to clamp this value to 0 instead of having a small number, which is non-zero.
That would be a reason not to use L2.
Yes.
Yeah.
Yes, exactly. Yes, Mark?
Patrick, did you have any evidence that's just stopping when you had a full rank matrix was the right place to stop in terms of zeroing, and you could go further and make the system overdetermined? And it might not be a bad idea since probably many of the links are really zero, and it just it just seemed to be somewhat arbitrary to stop there.
That's correct. So the first approach that we had, which was really to stop at full rank without using any regularization, the Schroen simulation performs badly, especially when there is a high number of loss rates, so the detection rate can get very bad. The other one, essentially, we keep. So it's true. We stop at the rank, but we keep the same regularization for the second step. So I guess all this, I mean, the problems linked to the noise in the measurements will be taken care of at the same time. That's the best I can say for that. But we didn't look too much on. I mean, so in theory, we didn't look at all at the influence of noise in the other than using this approach.
A related question. Did I see correctly? It looked like you had L1 norm on both your error term and
Yep.
on your penalty term. Are you using, so why are you using that second error term? Because, or that L1 term? Because
In the second one, or the first one?
well, so you have the penalty term, and you have what would usually be a squared error if you're doing a least squares type approach, and you had a 1 there as well, right? So that's usually used for a robust regression. Are you doing it because you feel robustness is needed for the noise term and the measurement noise?
Yes.
Because you've also mentioned the issue of numerous times, going back to Walter's talk, of course, too, with the routing matrix
Yes.
being noisy. But that certainly isn't going to a priori handle that, right? The issue of having operator noise in addition to measurement noise can be very
Yes,
subtle.
this-
I was wondering whether you knew somehow a priori that L1
No.
actually helps with that, or okay, you just
No, this and we did the two. So with the two, so the penalty term is always with one norm, and the difference Rx minus Y with the two norm and the one norm, and got better results in general with the one norm than with the two norm. But as far as I can tell.
You seem to have a linear relation between the variance in of the rate of the loss rates and the loss rates. Did you explore that possibility, or
No,
that could give you the equation needed, basically saying that you.
it's I mean it's roughly linear, but no, we just use it for monotonicity. It's true. You could use that. It's true. Yeah.
Just justifies your use of.
Yeah, exactly.
Yeah.
Exactly. But it's true that we could probably extract more information from these relations. But correct.
Okay, well that wraps up.
Thank you.
Very interesting talk to wrap up the session.